sometimes it slips my mind. Like all of you, I myself got quite a lot on my plate, so there is a remote chance I forget to start the recording, but now the recording is set. Right. So I'll come back to my questions. If you've got any questions or comments or something like that, feedback. Do you need to ask me anything? Okay, fine. I suppose not. Not at the moment, at least. But feel free to. We've got a WhatsApp group, haven't we? Do you know about the WhatsApp group? Huh?
No.
DCR. Okay.
I'm not in it.
Sorry? Can't hear you.
I'm not a member. I'm not a member.
Oh, you're
of
not
that
a
group.
member. Okay, fine. Probably.
I'm not a member either.
Yes, I'm not sure we have made the group.
Must be okay, fine. So I have to let me prepare the group for you because we're just a few people. So if you need to communicate with me, you can do it. Right? It's
Do you
good to
have our phone numbers?
Sorry?
Or do you have
No,
our?
I'll send you a link. No. You
Ah,
know,
okay.
I'll send you a link and you can join. I'll issue the link, send it over to you. Well, I suppose I haven't got the group here any longer. I must have deleted it from last year. So I have to make a new group. Never mind. But I think I need at least a number. New group. At least one contact must be selected. Now, who's going to be that contact? I probably need a number at the moment so I can start the group.
I can tell you my number.
Okay. I think I first need to register you in my contact list. Hold on.
Okay.
So contacts, new contact, Google, find
Andrei Peșleagă.
Andrei Peșleagă. Yeah, I can see your name. Thank you. And your phone, please.
078.
Yeah.
440.
Yeah.
54.
Yeah.
64.
Okay, so I'll repeat.
I made a mistake. It's 5564.
Okay. So 0784 405 564. That's true?
Okay.
Okay, fine.
Yes.
So I'm saving you. You've got WhatsApp, I see. So that's fine. Thank you. Okay, Andrei. So I can easily find you. Oh. Why am I not seeing you in the WhatsApp list? What is this? Huh?
Close the WhatsApp. Close WhatsApp and
start
open it again.
Yeah, start again.
Yes.
Give me a sec. New group. You're still not here. Oh, wait, sorry. It's AL. You're AN. Oh, yeah, you are here. Okay. So it's just you in the group for the time being. This is DCR 2021. Okay, fine. Creating the group. Cool. Now, more. How do I get the link? Group info. I think it's in the group info. Group info. Invite share. Yeah, thank you. I can see you. Invite via link. Share link. Let's see if this guy is smart enough. Teams. No, not Bluetooth. Sorry about that. Try again. Share link. Teams. Channels. Okay. I can't see your channel. Shit. It's not here. Reducere. It's in Romanian, I think. Oh yeah, there you go. Shoot. I have to try again. Stupid phone. Yeah. Can you see in the class? Can you see the link in the Teams?
Where?
In the Teams class, in the chat of the class.
No.
I don't think it's there yet.
A link. It's only a text.
No, it's a link. So you have to go to the class. Look.
Ah, okay, it's there. It's
No,
there.
it's there. Look, it's there. Just click and register. Okay.
Okay.
Okay, register. I think everything's fine now, yeah? Okay. It's okay, yeah?
Yes, it's good.
Okay, fine, good. So now you can use this channel to this WhatsApp group to register and notify me about any issues that you have, okay? The minute you encounter some problem, please feel free to tell me, okay? Make me aware of it. And I can fix it as soon as possible, okay? Right, let's go back to our class. Right, so last time we were discussing about this property of controllability, and finally we showed that once you have any pair of matrices A and B, okay, then using a coordinate transformation T through this controllability decomposition theorem, we say it in Romanian here, TDC, so it's easy to use this acronym. You can always go back, you can always find a pair AB, which is still not controllable. However, with a special structure, such that this pair A1, B1 is controllable. Okay? You can do that. You can easily do that. Okay? We are not going to do or to read or to check the proof. We take it for granted, okay? But it's possible, okay? It's possible. Okay. Yeah. So the remarks about this issue, about this property, is that you can always find an input-output equivalent system which is controllable, okay? The controllable decomposition is built in a certain fashion, okay? So you can easily extract a coordinate transformation up to a certain you extract a part of the R, okay, of the controllability matrix, and you can build up a coordinate transformation such that this thing is applied, okay, such that this thing is applied. I'm not going to make an example of that because this is not the issue for this class, okay? So we assume, and MATLAB can do that, when we are going to learn about minimal realizations, there is MATLAB who is going to compute a minimal realization for your system. This is not a dynamical systems class as it is. This is about model reduction. So I'm not interested in showing you a particular algorithm of constructing extracting the controllable part out of any pair of matrices. Okay, so that's possible.
Just a moment.
Yes,
I'm not sure if we can see the screen. The share.
Sorry, forgot to. Why did it stop? Because I started. Why not? Because I can see it. It's shared.
Okay, maybe it's my fault. Then I will check.
Your other colleagues, Andrei, other people. Dan, can you see the screen?
Yes, I can see.
Yes.
Okay,
Yes.
so the other screen. So there's probably an issue with your
Okay, sorry for interrupting then.
No problem. No problem. Feel free to interrupt anytime. I don't mind. We are. This is a master's class, so it's more like a discussion forum. This is not the classic bachelor class where I talk, you listen, and that's it. No, you can always interrupt me. You can always ask me questions or address issues. I encourage this. Okay, so feel free to interrupt me anytime. No problem. So where were we? Oh yeah. Like I said, I'm not interested at this moment because I can make here, of course, I could waste the time and show you an example how to build this T, how to build this matrix to construct, to achieve this this special block triangular form, but this is not important because this you can do in MATLAB very easily. But it's important to understand what happens, okay? So how to get lower dimensions, that's the idea. But this can be done in MATLAB. This can be done in MATLAB. So there is no point in talking to you about these particular algorithms, okay? But we have to understand that it's possible to do that. It's possible to do that, okay? Furthermore, controllability is invariant with respect to space equivalent, which is a very powerful result. So changing the coordinates is not affecting stability because it's not changing eigenvalues, and it's not affecting controllability also, again, because it's not changing the eigenvalues, okay? So you have to understand that for a matrix or for a linear application, it's not the form that it's important, but the content, okay? And the content, the basis of a linear application is the eigenvalues of the matrix. That's the heart and the brains of a linear application of a matrix. It's not the numbers that are important, but the eigenvalues, okay? So it's not the numbers in the matrix, but the eigenvalues, okay? And we were talking about the fact that controllability is generic, and I was asking you last time to perform an exercise in the sense that you can generate using the rand function a couple of matrices A and B, and then you can check the controllability of the matrices A and B. You have to watch out for dimensions. A and B should have the same number of lines. A should be square and B can be anything, okay? Can be a vector, narrow or wide. That doesn't matter. And you can check controllability, okay? And you'll see that if you every time you run your script, every time you run your script, you'll probably never run into an uncontrollable pair of matrices, okay? Okay, and we were saying that it's also possible to come back from a specific state back to the origin via some prescribed input, okay? So we can do that. We can do that. And that's called reachability. And I was telling you last time that this is specific to linear systems. It's peculiar to linear systems. However, highly improbable and not true in the nonlinear case, where the two properties are actually kind of different, okay? Of course. Now, the dual of this controllability, so we were checking, at first we were checking this relation, x dot is ax plus bu. So we are looking controllability input u to steer the state x, from the origin up to a certain coordinate. Now the question is, let's look at the other part. Let's turn off the input. Turn off the input. Turn off. Yeah. And let's look at the autonomous system. X dot is ax plus bu. Okay, with the initial condition x. Okay. And let's see what happens to the output. Let's see if we can find the x, the influence of x on the output y. Is it clear? So controllability is about you steering the state. You turn off controllability. This is important because we are going to talk about the Hankel operator at a certain point, and that's quite relevant. Okay? So you turn off the input and you check the influence of the state x, where your system was brought by the controllable input. You check the influence of the state on the output. This is called observability. So you need to check if the state is observable. Okay, so it can be noticed through the output measurement. Remember that, or recall that usually the states are those quantities, those time functions, which cannot be measured in the system. The only thing we can measure in the system is the output. Okay? Outputs are signals. These are measurable signals. What cannot be measured is usually put in the belly, inside the dynamical system. It's influencing the dynamics more or less, okay? Cannot be measured, but has an important, it's very important, okay? And its importance can be looked at the output of the system, okay? Observability is also a qualitative property, just like controllability, and it's of the whole system. Measures the possibility to find the state by measuring the output y. I think this is quite clear. Okay, so you measure the output y, and you can say something about that particular state. Of course, observability is related to the free evolution of the system. Makes sense. So you turn off the input, that means 0 input signals, and you look at system number 7. System number 7. Okay. So as you can see, observability is a feature of the pair C and A. And please notice the order or in the pair, output dynamics, okay? Now, if you have this system, you remember that the solution of this equation, okay, is x equals e to the power at x0. This is the solution of this equation. We know that, okay? So the output is just multiply this with c, and this is issuing the output y, the measurable output y, okay? So from 7, we can easily get number 8, okay? For at any moment in time, tau, non-negative, okay? Any moment tau non-negative, okay? So c e to the power at x naught. Now the question is this output 0 or not? That's the question. Is this output 0 or not? Okay. So since this is related to influence of the output, okay, in the measure, when you measure the output and you check the influence of the state x naught over the output y, okay, that's what you do. This is what this property is all about, okay. It's easier to introduce the opposite, okay, because our mind processes such information much easier when you do not see instead of when you see. This is much easier. Check it out. So it's easier to introduce the concept of an unobservable state. A state is called unobservable at any time t positive if setting the initial condition of the system at that state x, the free evolution of y is identical to 0 on this interval, okay, with is 0 on this time interval using this formula, okay. So observable is simply is achieved simply by denying through the denial of this unobservability property, okay. So a state is unobservable if the output is 0 when in the free evolution of this specific system, okay? That's what it means. So unobservable, essentially, unobservable means if y of t in 8, okay, is 0, then x is non-zero. You see? So the idea is that if unobservable, if y, if I was trying to write the formula, if c e a t x equals 0, then x is non-zero. This is unobservability. This is unobservability. Okay, this is how you check it. You look at the output, okay, and if you find that the output is 0 for that non-zero state, then the state is unobservable. Okay, then the state is unobservable. Of course, the observability is benefits from the same properties, just like controllability. We can define the so-called observability gradient. Observability gradient at a moment in time t positive, which is defined by formula number 9. Okay. Note that the way this matrix is constructed, it's easy to check that this matrix is a symmetric matrix because the transposition operation commutes with the integration. So, and then everything is just following naturally. Okay. This is also a semi-positive definite matrix at any time t, by the way it's constructed. Okay. So again, since this is true, we can again split this matrix, okay, the evolution of this matrix into the kernel of this matrix and the image of this matrix. And I recall that last time we explained what an image and the kernel are. Okay. So the kernel of the matrix is probably going to be very important in this case. Okay. And we have an important result. Consider a moment in time t positive fixed. Okay. The state x is unobservable if and only if x is in the kernel of this matrix, okay? Because that's what we are discussing. CEAT x is 0, okay? Okay, so if x is non-zero, that means that x belongs into the kernel of something. Okay, x belongs belongs to the kernel of something. Okay, so the output is 0, the state is unobservable, so this output is 0, if and only if the state vector x is in the kernel of this matrix. Okay, of course the state is unobservable if at any moment in time, if it's unobservable at any time t positive. Okay, so observability is related to the kernel of the controllability of the observability gramian. Remember that controllability, a state was controllable if it was, if it were, or if it is, it's controllable if it's in the image of the controllability matrix. Here we talk about the kernel of the observability gramian, and of course we are going to have, probably you realize we're going to issue an observability matrix as well. We also have an asymptotic observability gramian. So we set t in this formula. We set t to go to infinity, okay, and we get the asymptotic observability gramian, or the observability gramian in infinite time. So assuming the matrix A is asymptotically stable, so the spectrum of A, the eigenvalues are in the open left half plane, then there exists such a limit, and it's finite, and it's denoted by the matrix LO, which is a square matrix, and it's called the asymptotic observability gramian. Okay, this gramian is the solution of this Lyapunov equation. We remember Lyapunov equation from the stability discussion, right? Hence, this matrix, matrix equation has a solution, and a unique solution, if A is asymptotically stable. You remember the result at the end of the previous chapter. Okay, that result was telling us, okay, this matrix here, C transpose C, this is a semi-positive definite matrix, rank deficient, of course. It's never going to be strictly positive definite, but it's semi-positive definite. Okay, it's semi-positive definite. This is Q, if you remember, the Q. Okay, so explicitly, the solution of such an equation, okay, the solution of such an equation is LO, this matrix, which is the asymptotic observability gramian. Okay, now if the pair CA is observable, okay, and we'll discuss what the pair CA is observable soon, then this matrix is positive definite. Okay, LO is positive definite, and this the observability gramian is the solution, the unique solution actually, of the Lyapunov equation. Okay, now if we have any arbitrary state, okay, we can uniquely decompose each state into a part which belongs to the kernel and a part which belongs to the image of the matrix. Okay, so this is X image and this is X kernel. You can do that. Okay, the direct sum, so just remember that if CA is observable, the kernel of LO plus the image of LO plus, like this, is the whole state space Rn, okay, when the pair CA is observable. Okay, oh, it's written just like here, so I can delete this. It's written here, and this is true because you can always write the state space, which is Rn. You can always decompose it like that. Hence, look, the output, which is CE to the power ATX, you split x into xl plus xk, then you get this part. Now, I said that x, how is xk if it belongs to the kernel of the matrix? How is xk? Observable or unobservable if it belongs to the kernel? How is it?
Unobservable.
Unobservable. Hence, what is CE to the power ATXK? How much is this if it's unobservable?
0.
0. So you're left only with this term. It's 0. True. Very good. Very good. Okay. Right. So we have now to understand what an unobservable space is. Okay. What an observable space is. So you construct this matrix Q. Okay. And you denote by nk the kernel of this matrix. This is called an observability matrix. Okay. And the unobservable space respectively in k steps. Okay. In k steps. Yeah. So with this nk has the following properties: is the intersection of all the kernels of these matrices. Okay. Okay. So it's the intersection. Once you make this decomposition, you can always you can take the a out. You can do it like this, and then you get this property. Yeah. This is not A inverse. Look out here. This is about something else. Okay. So you can have all these nice properties, and all these unobservable spaces are nested to each other. Okay. So you have a chain of subspaces. Okay. So there exists an integer mu. Okay, such that this property down here holds. So based on this property and on the kernel issue that this property has, you can always find these very nice features to use for later study. Furthermore, the limit when k goes to infinity to this is actually going to the unobservable state, unobservable space, sorry, of dimension n. Okay, mu is called observability index. Okay, and mu equal to n, it's called the unobservable space of the CA pair. Note that n is the kernel, the unobservable, the whole unobservable space is the kernel of the observability matrix Q. Hence, you get all these properties, and you get this invariance property. So n is a invariant contained in the kernel of the matrix C. This is an invariant subspace. Okay, so the unobservable space is an invariant subspace of the kernel of the matrix C. Okay, and has also this property that actually it's the greatest A invariant subspace contained in the kernel of C. Furthermore, we have now to emphasize another peculiarity of linear systems, only of linear time invariant dynamical systems. Nonlinear systems, I'm not sure if infinite dimensional systems or other types do benefit from this property, but I'm sure that the linear time invariant systems do. Okay, it's called duality principle. So the properties of controllability and observability are actually dual to each other. This is it says here a fundamental principle in the theory of dynamic systems. Okay, of dynamical systems. So the controllable subspace in k steps of the pair AB is the orthogonal complement of the unobservable subspace in k steps of the pair B transposed A transposed, you see? So you can write it like this. In particular, the pair AB is controllable if and only if the pair B transpose A transpose is observable. This is very important. Very important. Okay, and vice versa. If the pair CA is observable, if and only if the pair A transposed C transposed is controllable. Okay, so these properties are dual to each other. This is very important. We can also have this type of criterion. So a pair is observable if and only if this rank, the rank of this matrix, is n for all S in C. And actually, since you have for all S in C, the only problem when this the rank might drop, the only issue is actually you verify you verify this property. You verify this property only for S in the spectrum of the matrix A, because that's the only problem when the rank of this part can drop. That's the only time when the rank of this part can drop. So you usually check for the eigenvalues in the spectrum of the matrix A. Okay, and here then you can get the notion of observable and unobservable eigenvalue. Similarly, for controllability, you can check if an eigenvalue of the system is controllable. So you take this, you can check this property, rank Si minus A concatenated to B, extended with B, if this is N or not. Okay, so if this is N, this means that S is a controllable eigenvalue. Okay, so you can have also the eigenvalues of the system benefit from controllability and observability. Okay, so you can have controllable eigenvalues, uncontrollable eigenvalues, observable eigenvalues, unobservable eigenvalues. Okay, and you can check it using this type of Popov-Belevich-Hautus. That's what PBH stands for. It's 3 names. Okay, for an eigenvalue of the matrix A. Okay, so we can have the notion of an unobservable eigenvalue. Okay, through duality, we can also have the notion of an uncontrollable or controllable eigenvalue. Okay, now this is very important because we are going to study the degree, if you like, of controllability and observability of each eigenvalue or state corresponding to an eigenvalue of a given system. And based on that, we are going to build up an approximation, neglecting the dynamics which are hardly controllable and hardly observable. We are going to keep only the dynamics which are easily controllable, so not too much effort, and have a big influence on the output, so they are also easily observable. This is going to constitute the basis of the balanced truncation model order reduction technique. Okay, so this is very important. Since we are talking, we have discussed about the duality between the controllability and the observability of an ABC system, it's only fair to discuss about the observable decomposition of a system. We had a controllable decomposition. Now I told you that these properties are dual to each other. Okay, if they are dual to each other, that means that in a dual sense, there exists an observable decomposition. So there exists a coordinate transformation which can be applied on an ABC system, bringing the ABC system into a specific block triangular form where we can identify the controllable parts. We can the observable part. Okay, so there exists a state space equivalent A hat, B hat, C hat, D of this form with the coordinate transformation T, okay, such that the pair C2A2 is observable. So that can be done for any dynamical system characterized by these 4 matrices A, B, C, D. Moreover, all these systems are input-output equivalent. These systems are all of them input-output equivalent. That is, this property holds. So the input-output important part is also always given by the observable part and by the controllable part as well. So now it's interesting to see what is the controllable and observable part and what does it actually mean. Probably this is going to be very important, and we are going to discuss that quite soon. Okay, we're going to discuss that quite soon. So we can easily have an observable decomposition, okay, just like this. So you can always build up coordinate transformation such that the pair C2A2 is an observable pair. Okay, and easily compute your the transfer matrix of your given system, because it only depends on the observable part of the system. Now, we can also have an alternative, a completely equivalent version, where we can build the coordinate transformation in a different fashion, similar to the previous one, where you can have a block inferior, block lower triangular form, where the observable part is issued by these three quantities here. So you can easily find the coordinate transformation to get a lower block triangular form. And in this lower block triangular form, you emphasize the observable and the unobservable part of the system. In this form, the pair C1A1 is observable, and all these systems are equivalent to each other. All these systems are equivalent to each other, and the transfer matrix can be easily computed only based on the observable part of the system. What does this actually mean? So we were saying that we can measure the outputs. Okay, fine. But in these outputs, if you can identify the states which are non-zero but issue or yield a zero output, then these states do not have any influence on the input or on the output behavior of such a system. This is the idea. Okay, so even if you have many equations, probably part of these equations are not relevant for the output. This part of the dynamics is not relevant for the output, is not doing anything for the output. Okay, hence it can be completely eliminated. That means that you can rewrite the same system that you have with a lower number of equations. The same holds for the controllable part. You only pick the controllable part. That means that the only thing which is relevant from an input to state behavior, that thing is actually the main dynamics of the system, which represent and define your system. Okay, the rest can be thrown away. Because the uncontrollable part cannot be modified in any way by any input whatsoever. Okay, that's the idea. Now I have to stop for a second and ask you if you people understand what I'm talking about here.
Yeah, we can follow you.
Okay, you can follow me. Okay, that's good. I only advise you, people who come from our faculty, please go back to the second year automatic control systems theory. Okay, DCR second part of the course. The rest of you can look in the book of Antulas. You see much more details about these things in the book of Antulas, which is uploaded on Moodle. Okay, please try to take some time and do some extra reading to understand these things, because this class is it's only a recap, a review, an overview of the theory here. I cannot go and start doing examples for this, because this is not the scope of this class. The scope of this class is to build approximations for these systems, okay? So please try to do some extra reading to understand these things. And the book of Antulas, I think it's a wonderful handbook to fix, to understand, to grasp the meaning of these notions, okay, and properties. Now, you can have, finally, you get to the point where you can have what's called a structural decomposition of a system. Okay, so you can identify, since you can build a coordinate transformation that identifies the observable and unobservable part. You can build a coordinate transformation which identifies the controllable and uncontrollable part. The question is, can you build a general coordinate transformation to identify the following: observable and unobservable, observable and controllable, unobservable and controllable, okay, uncontrollable and observable, and finally, the controllable and observable part. Can we do that? This is the question. Can we identify this puzzle? Can we make these prop pieces? Can we put them together and make this puzzle clearly identify these specific parts? That's the question. The answer is yes. How can we do that? The mathematical result or the theoretical result is quite involved, but it's a very strong result. And the numeric and the application procedure is merely combining the controllable decomposition and the observable decomposition and uniting these two. Okay, so accumulating the transformation. This is how things are done, and this will lead us to a second very important, or to another extremely important notion, which is the basics of this course, the notion of minimal realizations, yeah, of minimal dimension and minimal realization of a given system. Okay, so now you have a general system ABCD, and you consider the controllability subspace of the pair AB and the unobservable space of the pair CA. Okay, note that you can build the following spaces. You can have the intersection of R and N, and you get the space X1. Now this is unobservable and controllable. Okay, unobservable but controllable. This is 11. Now you consider you have the spaces X2 and X3, which are the complements in R and N, like this. Okay, R is X1 direct sum plus X2, and N is X1 plus X3. So now you have what? Uncontrollable but observable. Okay. No, sorry, it's not that. What do you have now? So this is R, they are all controllable. So this is controllable, okay, and observable, unobservable, all of them, okay. This is unobservable but controllable or uncontrollable, okay. Now all of them, these are the state space, the whole state space is the reunion of these two sets and the direct sum of this part, which is the most important, controllable and observable. Controllable and observable. Okay. Note that these subspaces X2, X3, and X4, they are not uniquely defined. Okay. So we split up the state space essentially into these four sets, which actually, because of the previous properties or how these sets are built, because of how these spaces are built, you can have the direct sum of all the four subspaces to form the whole state space of your system. Okay. Now we have some properties. This property, which is invariance, so the controllable space is in subspace is invariant. Okay, and the image of the matrix B is in this controllable subspace. The unobservable subspaces we have just discussed earlier, as we just discussed an hour ago, is also invariant, and moreover, it's included. The unobservable space is included in the kernel of the matrix C. Okay, so this calligraphic I is actually the image. Yeah, this is the image. Okay, hence you get this invariance property of the space x1, and furthermore the space x1 is included in the kernel of the matrix C, and we consider the basis matrices for each subspace. Now, with this basis, you build up this matrix coordinate transformation T. You build up T like this. You build up T like this. I think this should be like this, actually. Okay. So you build this matrix T based on the property and the way these spaces have been built. Okay. So you see this is an accumulation of transformations. This is an you accumulate transformations one after another. You just multiply them one after the other. Okay. Look, and now with this coordinate transformation, you apply it to your original system, and then you get this specific form in 19. This is a very peculiar form. You see all these puzzle blocks like here. Okay. Right? With these things all follow from these relations 11 through 18. Okay. And now you get, if you apply on this the controllability decomposition, you get the controllable part, which is given by 20. And from the observability decomposition, you get this observable part, which is number 21. Okay. Now, to test the pair 20, okay, you use the PBH test, we just discussed earlier. You use the PBH test, which is this one, okay, which is this one for the pair 20. Okay. Once you apply this PBH test, you realize that the dimension of this matrix is the dimension of the space X2. Okay. Hence, the pair A22B2 is controllable itself. Look, this guy is totally controllable. Okay, but now using the PBH test, you can prove that this part is also controllable. Only this part is also controllable. Okay. Now the same using the dual for this. So this is completely observable. This guy is totally observable. That's what we discussed from applying this coordinate transformation. However, also you can check that this particular pair is actually observable as well. Yeah. So A22B2 is controllable. C2A22 is observable. So using the test, therefore this subsystem is both controllable and observable. So this part A22, B2, C2, and D form the observable and the controllable part of the original system. Okay. And finally, note that the transfer matrix, so the input-output behavior, is uniquely related, bijectively related to the controllable and observable part of the system. What does this mean? That if you have a number of equations, only the controllable and the observable states, so only that number of equations, which is controllable and observable, really counts when you put an input and you measure the output of the system. That's the only dynamics that count. This is the only dynamics that count, the controllable and the observable part. This is what matters. This is what matters. Okay? This is what matters. Note that the dimension of A22 is much smaller than the dimension of A or A hat. Okay? It's smaller than that. Okay? And this is very important. So overall, once we have all of this, we can have the following main result, which is the so-called structural decomposition theorem. If you have an arbitrary system A, B, C, D, it is state space equivalent to this A hat, B hat, C hat, D with the structure 19. This is structure 19. With the structure 19, this puzzle-like structure with this very relevant and theoretically clear sparsity. Sparsity is the key in this problem. Okay. Where some blocks may be void, so some blocks can also be zero. An input-output equivalent with the controllable and observable system A22, B2, C2, D. Okay, so this is a crucial result telling you that based on these two structural properties, controllability and observability, you can reduce, or you can these guys are the controllable and observable. The observable part has the influence on the input-output behavior of the system. The rest do not matter at all. The rest do not matter at all. Look that this has no relevance. Note that all these properties, all that we have discussed so far in this chapter, has no connection to the stability. Keep it in mind. There's no connection to the stability whatsoever. Okay, there's no connection to the stability whatsoever. Okay, so we can have controllable, observable, and finally the whole decomposition, okay, into controllable and observable part. Now, in the following chapter, we are going essentially to focus on the analysis of this part. Okay, and we are going to wonder, ask ourselves, if you have given such a matrix T of S, yeah, given, does there exist A22, B2, C2, D? And how to compute this? How to find? Okay. Another question, is there another A22, B2, C2, D of smaller dimension? Now this is called, all of this is called the realization. The realization problem of TS. These are the main questions we need to respond. We need to give an answer to. You probably realize that the answers are positive, all of them. Okay. Indeed, there exists, and probably not only one. Is it unique? That's another question. Probably not. How do you find it? We'll see. Is there another one of smaller dimension? Probably no. Okay. How do you get all these things? Okay. Once you have the T of S fixed. This is what we are going to discuss next. Now, I'm going to ask you to have a short break so I can set up the next chapter. Okay. So let's have a break. Is that okay with you?
Yes, it's fine.
Okay, but before we go for the break, have you got any questions about what we have discussed so far today? Any questions or issues? Questions or issues, please? I suppose not. I'm still here anyway. Okay. Break if you like. Right, so I'm back. Let's start, shall we?
Yes.
Okay, fine. All right, let's move on. So, what have we discussed in the previous chapter so far? Structural properties of state space systems. They are basic properties of the dynamical system, which play, they say here, a major role in the analysis and design of control systems. And of course, also, since we talk about analysis, it's also going to be quite helpful in approximating linear time invariant system with smaller linear time invariant systems. Okay, so we have controllability, observability, minimality, etc., which they are yielded by what have I done here? I think I made a mistake. Now I'm looking. Is it just repeating itself? Apparently so. I'm sorry, I think I made a mistake here. Should be a different file. Sorry about that. Let's try again. Okay, what's going on here? So this is there's 3. Let me check something. Two. This is 3. Okay, here should be 4. Sorry. Was the wrong file. I'm just going to make it right now and upload the proper file, so it should be number 4. Okay, yeah, now it's the right one. Sorry. So state space systems, and so we discussed structural properties, and now we have to discuss about the issues of the transfer matrices. Yeah, because we saw that the properties, controllability, observability, they are completely related to the transfer matrix of a system. So let's just recall a few things. Any dynamical system of the form 1 with the initial condition xt0 is x0, it's linear, time invariant, causal, and finite dimensional. In particular, this is a convolution system. We proved that, having the transfer function matrix given by TS, by this formula. Okay. This denotes the input-output behavior, says here, under 0 initial condition. And all the entries of this transfer matrix, they are all rational complex functions. Okay. Now we have to start. So we know that once we have 1, we can easily go to 2, to this one. The question is, can you do the other way around? If you have this already given, yeah, from data, from whatever system identification, something like that, okay? If you have this, can you do the writing of these 4 matrices? Can you recover the differential equations from this system? And if you can do that, is that the lowest dimension and the lowest number of equations you can use? Let's have an example first, okay? So assume you have the TS. Let's take the single input, single output case. Case. So you have this. You have S plus 1, and here you have S squared plus S plus 1. You have this transfer function from data. You just compute it. You get this transfer function of your given process. Okay. So can you recover from this the differential equations? Usually what you do is this. Since this is a transfer function means the quotient between the output function and the input function. Okay, where the ys, where ys is the Laplace of the output signal yt, and us is the Laplace transform of the input signal ut. Okay, these are given. Okay, so you measure the output, you have the Laplace function of the output, you have the Laplace function of the input, and you have the transfer function between the two. The question is, can you write here a dynamical system? Well, let's see the easy way. Now, from this relation, this is equivalent. We know this from simple mathematics. You can multiply the terms like this, right? You can do this. True? This is very easy. Okay. Now, you just open the brackets here. You just open the brackets. So you have SUS plus US is S squared YS plus SYS plus YS. And now you simply use the Laplace transform table. Do you recall the Laplace transform table? Have you used this before?
Yes. At this.
And your friend here, have you used Laplace before? Do you know what this is?
No, I didn't use it.
You didn't. Laplace. So Laplace of a function of time is a so-called integral transform. It's integral from 0 to infinity, from ft e to the power minus st dt. This is what Laplace is. Okay, this is what Laplace is. It's an integral transform. Okay, you can find this anywhere on the internet if you need to look. To understand the things, you don't need to compute it. Okay, and it has a lot of properties which can be found in tables. Table of properties. Nobody learns them by heart, but everybody is using the properties. Okay, for instance, the derivation property. Okay, so Laplace of f prime t in S. Okay, so denote Laplace ft s is fs. Okay, then this is S times SF minus F0 plus. Okay, now when this is 0, so this is the important term. Okay, this is a property, and so on. Laplace F twice T in S is S squared Fs minus S F prime 0 plus minus F0 plus. No, SF like this, sorry, the other way around. Okay, it's like this. So again, this term. Okay, so these are in tables. You can find these in the tables. You can actually prove them if you know how to calculate this integral. This is not very difficult. Okay, this is called the Laplace transform. Now, you recognize here the terms from the Laplace. Okay, so you can apply on this relation here, you can apply the inverse of the Laplace transform. It has an inverse, okay? So if LFS is this, okay, that means that F is Laplace inverse from Fs in the point T, okay? So we know that, so now we can apply the inverse of the Laplace and get the equivalent form. Now, SU Laplace inverse is what? Look at the relation. What is that? It's clear that you have these guys equal to 0. So what do you get now? U prime T, true, if you apply inverse Laplace on this term, okay, on this term, plus U of T, okay, equals Y double T plus Y T plus Y T. You see? It's like this. Okay? It's like this. Right. So now you make from this this is a differential equation, a second order differential equation. Okay? This is a second order differential equation. Okay? Now you have to make this a system of first order differential equations so you can get A, B, C, D. So x1 equals y, which means x2 equals y dot equals x1 dot, which means nothing, and that's it. Okay, and that's it. Okay, so now from this guy you get this further means that y double dot t is minus this plus this plus this. Okay. Okay. So the first equation is x1 dot equals x2. The second equation is x2 dot. x2 dot means y double dot t is minus x2 minus x1 plus u dot. Okay? All right? And now you assume that you pick the output y being, for instance, x1. So this is 1, 0 times x1, x2. And a, b, c, you get a equal 0, 1, minus 1, minus 1, and b equals 0, 1. Okay? Oh, so you can write two differential equations. You can write two differential equations, okay, that give you this transfer function. So we started from this transfer function, And we ended up with these matrices A, B, and C. Okay, A, B, and C. Okay, we ended up with these matrices. So yes, we realized TS. Yeah. So this is a realization of TS. Question: is this unique? What do you think? Is this unique? What say you?
I think it's not unique
No,
because
it's not unique. Why?
you use the trick. You decide what to be the state.
Exactly. So, but now you learned about coordinate transformations. So you can apply an infinity of coordinate transformations and get an infinity of matrices A, B, C, which mean the same thing, essentially, which have all this unique transfer function. Do you agree? You agree, right?
Yes, yes.
Okay. So, yes, there exists. So that's the question. The question is, can you get from this guy to this guy number one? And the answer is positive. Yes, you can. This is called the problem of realizability of a transfer matrix. So the natural question you address is, assuming the transfer matrix of a multiple input, multiple output system, that the example that we showed was very simple, is rational and proper. Proper means that, so if T of S is AS, no, it's BS over AS, is proper if the degree of B is smaller than the degree of A. And this is the good case. No, it's actually proper if this is true. Then you have strictly proper if deg B is strictly smaller than deg degree of A. And improper if degree of B is larger than the degree of A. And this is not good. So we are working in this case, the proper case. This is proper and strictly proper case. Okay, these are the cases which interest us because these are the physical cases. Okay. So assuming the transform action of a MIMO system is rational and proper, can we describe the time domain, the dynamical evolution through a model 1, through this? This is the natural question. More precisely, knowing that TS is a proper rational matrix of dimension Pm, so P outputs, M inputs, can we find 4 matrices A, B, C, D with these appropriate dimensions, of course, such that the dynamical system has the transfer function like this? Okay. If so, and we noticed, we have already seen an example that this is possible, when such 4 matrices exist, they are called a state space realization of the transfer matrix T of S. And this is a crucial problem, and this is actually the basic problem, the basis for model order reduction, because model order reduction is quite connected to this problem. Okay, it's connected. If the realization problem has the same dimension as the transfer matrix, the model reduction problem must yield realizations which are of dimension much lower than the degree of the transfer matrix. Does this make sense to you?
Yeah.
Okay, so this is not approximation. This is the problem of realizability, which we try to recall now. There are a few natural questions we need to address. Is there always a realization? Yes. How can it be computed? We'll see. Is this realization unique? No. No, because there are coordinate transformations. So each realization you compute is one of the infinite many realizations you can compute for a given transfer matrix. Is there a realization of minimal or maximal dimension? Of minimal dimension, yes, and this is the crucial problem we address here. Minimal and yes, this is the crucial problem we address in this chapter. Maximal, no, of course not. You can add up as many junk equations as possible. You can add them up, an infinity of them. That's not an issue, okay? So you can do that. But the minimal realization problem, that's a crucial problem, okay? How do we characterize minimal realizations? The minimal realizations are those who are controllable and observable. Those are the minimal realizations given by the structural decomposition theorem in the previous chapter. That's the main result that helps us compute the minimal realization of a transfer matrix. How do we get these minimal realizations? I just explained through the structural decomposition theorem. Okay. Are minimal realizations unique? No, they are not. They are not unique. What's the connection between two minimal realizations? They are state space equivalent. Okay, so there's an infinity of minimal realizations. Once you compute a minimal dimension, that's unique. So the minimal dimension is unique, but you can write an infinity of matrices that have that minimal dimension. Okay. So these are the natural questions to address, and these are the answers that we give. And now we simply solve these problems. So we solve this problem and this problem. So these two questions are the questions we address throughout this whole chapter of the discussion before we proceed with the model order reduction techniques. So we study the problem of realizability of a transfer matrix. We consider a transfer matrix of this form, which is a proper rational matrix. All the entries in the matrix are proper rational functions, satisfying this degree property. Okay, the degree of Pij is greater than or equal to the degree of Rij for all indices I and j, where we assume that, and also we assume that all the entries are irreducible to rational functions. Okay, since Ts is proper, we have that the matrix D is always T at infinity, is the transfer matrix at infinity, and this is a finite matrix. This is a finite matrix because this D is so this is the easiest to compute. D is always the first to compute. How? You take the limit to infinity in S of Ts. This is how you do it. Okay. Now you subtract this D from the original Ts, and you compute the minimal realization for the strictly proper function. So once you remove D from Ts, the proper function becomes a strictly proper function. Okay, that's immediately happening. Yeah. So now this, because D is 0 now, since you subtracted D, T tilde has this form, CSI minus A inverse B. And since it's strictly proper, we can easily split this into a quotient of polynomials. The numerator is a matrix polynomial, and the denominator is a simple classic polynomial. Okay, where gamma is the least common monic multiple yes, cel mai mic multiplu comun. Yes, least common multiple, which is a monic polynomial of all denominators present in T tilde S. Okay, and ki, they are constant matrices. So note that the polynomial from the numerator has matrix coefficients, okay? These are matrix coefficients and not number. So based on this, you can easily write a realization. We have simple formula giving us the realization. We have, for instance, a canonical controllable realization, making the matrix ABC just like this. Just like this. Okay, look at the formula. Look at the gammas, how you put the gammas here. So this can, okay. The question is, where does this form come from? And why is it canonical? That's the question. This comes from the fact that this polynomial here has an infinity of companion matrices. An infinity of companion matrices. Okay? So, if you have a matrix, a square matrix A, you have the minimal polynomial, which is this. Okay? Okay? However, if you have a polynomial of degree n lambda, if you have this, this has an infinity of matrices A such that P lambda is that lambda I minus A. Is this clear to you? This is standard mathematics. Okay. So a matrix has a unique minimal polynomial. However, a polynomial can be the minimal polynomial of an infinity of matrices due to coordinate transformations, of course. Okay. So look at this polynomial. This polynomial can have a companion matrix A. So from these gammas, you get the matrix A. And this is the matrix A, yielded by the gammas of the nominator. Why is that? Let's remember. I said that TS, okay, is C Si minus A inverse B. But what is Si minus A inverse? What is Si minus A inverse? What is this? This is 1 over that Si minus A. So this is the minimal polynomial in S of the matrix A times this guy, the adjoint, okay? So look, you have this nominator here. You have this nominator. So this is where this gamma polynomial this gamma coefficient polynomial comes from. This is where it comes from, okay? This monic least common multiple, okay? This is where it comes from. So you can build A like this. You can build B like this. You can build C from the matrix coefficients. Notice here the matrix coefficients. Look, from 2. Okay. And then you have your standard or your canonical controller form of the given transfer matrix. Is this clear? So you can easily write this formula. You can easily write this formula. Okay. True? Yeah. For instance, MATLAB can easily do that. MATLAB can easily do that. And maybe we can have a few minutes to check how these things happen in MATLAB. Okay. And now we have a proof showing that indeed this ABC in 3 is a state space realization of the given TS. Assume that you can build this vector of polynomials theta s like this. You can easily check that Si minus A theta s if you multiply Si minus A like this, is B times gamma S. B times gamma S. Okay, so you just multiply this guy, and then you get B, yeah, B gamma S. Okay, probably this is what happens. Let's see, why is that? S squared. Oh yeah. Okay. Right. Furthermore, you can say that theta, now you can have theta over gamma is Si minus A inverse B, is Si minus inverse B. So Si minus A, this is n times n, Im Sim Sk inverse Im. I was just trying to see how you multiply these guys, you know. Because this is an n by n matrix. Not sure if this is properly written here, but apparently you can multiply this. You can multiply this. You know, B is this guy with zeros. Oh, okay. So you just start from B gamma. It's easier to do it like this, I think. I'm just trying to understand this. So B gamma S is 0, 0, 0, and here you get the gamma. Okay, you get Im times gamma 0 plus gamma k minus 1 s to the power minus k minus 1 plus s to the power k. So you can do that. You see, this is B gamma. This is B gamma. Okay. Okay. P gamma. This is Si minus A times this guy. Because this guy is that Si minus A. No, with the specific Si minus A, sorry. With the specific Si minus A, yeah, that makes sense. That makes sense. With this specific Si minus A. So Si minus A here, it's this guy, okay? So if you multiply it with theta, indeed, in this matrix, yeah, now it's clear, okay? So then you get the first column of the Si minus A, like this. Do you understand? Now it's clear. Do you understand what happens here? Do you understand? So you have this specific form of the matrix A, and you write Si minus A. Si minus A. Okay? So that's, what is Si minus A? Is S minus Im 0, 0. Okay? And then you get S on each diagonal. Okay? And minus Im, and so on. And on the final on the final this, you get S minus gamma 0, okay, times IM, and so on, okay? And you multiply this with IM, SIM, SK minus 1 IM. You multiply this. Now, once you multiply this, this has to give only one column, okay? All right? And probably you end up with this guy, okay? You just have to do the computations, okay? You just have to do the computations using this particular shape of A, okay? And you can check this relation, okay? Now, this is from this, you can easily get this. You take this guy, you put it in with the inverse here. You take this guy, you put it at the denominator here. So you have this relation, and now you multiply it with C. You multiply it with C, and you get this guy. No, you multiply C with theta, and you get this guy. That's easy to find. C with theta, and you get this guy. C is this guy, okay? And you multiply with theta from this guy, and you get this relation. You get the denominator, okay? So you build up, indeed, you recover your T tilde S. So indeed, the ABC we have just defined is a state space realization from the theta tilde. This realization is already controllable because it's in a controller canonical form. This is already controllable. So that's why it's called standard controllable realization, okay? It can be easily tested using the PBH test. In general, the canonical controller form is not necessarily observable. It is not necessarily observable. However, it might be. If it is, then it's minimal. If it is not, then it is not minimal. Dually, we can write a canonical observable realization. You only set up this formula. You have the IP in C, and then the K coefficients go into B like this. The proof is similar to, because the property is dual. Observability and controllability are dual to each other. The proof is the same. You get the same result. In general, this realization is not controllable, okay? It says here that for rational matrices of arbitrary dimensions, in general, one cannot write down a realization which is both controllable and observable at the same time. So you cannot just extract the controllable and observable part simply looking at the coefficients of the numerator and denominator of TS. We cannot do that, okay? You need to build specific quantities. For instance, you need to build the so-called Markov coefficients, okay? So we study the relations between two realizations of a proper rational matrix. That's what we have to do, okay? First of all, both D should be equal. Now, you do a development of the T tilde S in the so-called Laurent series. This is something from complex analysis. Around S infinity. It looks like the Taylor series, but it's for complex functions. Okay? So you can get this form. So TS can be done in gamma 1 S inverse plus gamma 2 S to the power minus 2, and so on and so forth. Now, if you have the coefficients in 6 and using the form 2, which is this form, okay? So using this and the coefficients in relation 6, okay? You can easily identify the relation between the K coefficients and the gamma coefficients in this form. You see? K minus 1 is gamma 1, K index K minus 2 is gamma 2 plus gamma K minus 1 gamma 1, and so on and so forth. You see? You can get these guys. So the gamma coefficients, the coefficients of the Taylor series expansion, are actually related to the coefficients of the nominator of the transfer matrix in this form. These gamma coefficients are called the Markov coefficients of the rational function Ts, and they are important invariants for the transfer matrix. Okay. Note that if ABCD is a realization of T, you can write this form for S equal to infinity. You can write this form for S equal to infinity. This form here. So the Markov coefficients have a specific formula given by this guy. Again, remember, this is a Laurent series around S equal to infinity. Okay, so these coefficients uniquely determine a transfer matrix, okay? Irrespective of the realization, keep that in mind, okay? All realization of TS have the same Markov coefficients, which are identical to those of TS. They're identical to those of TS. And based on these Markov coefficients, we can build a so-called Hankel matrix of the system, which is very important when we are going to talk about balanced truncation. This is the Hankel matrix can be quite important, and it's also related to controllability and observability of a given system. I suggest we stop here with the theory for today. Do you agree?
Sure.
And have a few minutes of playing in the MATLAB. Okay? Let's play for a second in the MATLAB. I'm going to stop this screen. I'm going to get to another screen. Let's play for a little while in MATLAB. Just to see a few things. Let's see what we can find out. Okay? So bear with me for a minute, please. All right. Do you find these things interesting? I know they are difficult. I'm sorry to tell you this is not an easy class. Actually, to tell you the truth, you should be doing a lot of extra reading, and you should read that book of Antulas, because there you have a lot of explanations about these things, and do a little bit of study. But I suppose you haven't got too much time to do that. But I can't help it. This is the class. I cannot change it. Okay, these are the notions. These are the things. So you'll have to bear with me. I hope you do not get upset. Okay. Just bear with me for a second, please. Bear with me for a second, please. Just a second, please. 1 second, please. Okay. Right. Close this window. Now I'm going to try to share this other screen with you where the MATLAB is open. Can you see the MATLAB screen?
Not yet.
Not yet.
Not yet.
Not yet.
No, it'll come soon.
Right now, yes.
Right now.
Okay, fine. Let's try to make a new script because it's better to work in scripts. Should be doing something. Oh. So this is a new script. Let's see. So let's build a transfer function. Let's take the example we had earlier. How do you build a transfer function? H equals TF. That's the transfer function command. N and D, numerator and denominator. Now we have to define them. The numerator is, if I remember correctly, 1, 1. And the denominator is 1, 1, 1. That's the example we had, true? I think that was the example we had earlier. Let's see what happens. Let's run it. Okay. Let's first save it. This is the teaching. This is your folder. This is the simulations. Okay. Realization trial. Let's call it like this. Save it. Now it should run a little bit. Up to path. It's busy. Don't worry, usually MATLAB should be very quick with these things, but this station is very slow. However, I'm doing my job with it, even if I have to wait for a little bit. I hope you don't mind. If you mind, I can't help it. Sorry. You see the transfer function we had, h. Can you see that? Yes?
Yeah.
Right. Now, where is my... I need the editor. Okay, so now I'm trying to build the state space realization. So state, let's call it state S, or maybe state underscore S, or I don't know, system, something like that. System. Okay, so is TF to SS transfer function to state space, or I think it's N and D. You have to call the same. Oops. No, it's not. This is not correct. No, I think it's a bit different. I think it's like this. You have to call the four matrices A, B, C, D. I think this is the right. Oh yeah, you see? And you have the transfer. This is an observable. So it was much easier for him to write an observable canonical form. Look, -1, -1, 1 and 0. No, a controllable, sorry, a controllable. However, he had it written in this equivalent form with the coefficients, you see, with the minus coefficients of the denominator. Look at the denominator, -1, -1, on the first line. So this is an equivalent controller canonical form, okay? But it's still a canonical form. B is 1, 0, and C is 1, 1, okay? All right. I'm not sure if you can write help TF to SS. Let's see if we can ask MATLAB to write a specific realization which I have in mind for him. Nunden. No, they're all returned in controller canonical form. It says here, look, it's controller canonical form. Okay, so this is the controller canonical form. Okay, it's being a single input, single output system. This is since this is a transfer function, that means that HS is equal to H transpose of S. That means that the observable canonical form is obtained simply transposing these matrices, here. Okay. So now I need to build the. I would like to build the system. I would like to build the system. Okay. So what I'm going to do now, I'm going to make the sys SS. So this builds, okay, of the A, B, C, and the D I just made. Okay. So this is my system now. Look, you see, he built the object. He built the object called system. Now, let's check if this system is controllable and observable. Else CTRB. Let's see how we call this. So this CTRB returns the controllability matrix. So you can either call the pair of matrices AB, or you can simply call the number sys. Okay. You can also, and then we have the CTRBF function. This is a very efficient numerical algorithm to compute the decomposition into controllable and uncontrollable spaces. The decomposition into controllable and uncontrollable spaces. Okay. All right. So let's just first check CTRB, and then I'll show you how CTRBF works. Okay, so we have here R is CTRB sys. Okay, and this is the controllability matrix, and you can easily check that we can have here rank R, and the rank R is 2, which is the dimension of the system, so the system is controllable. Okay. Now we can compute also the observability matrix. Can compute the observability matrix. Q equals OBS sys. Oh, it's not OBS. I think it's OBSV. I think I made a mistake. Let's correct it. OBSV, then we have a far. Look, this is the controllability matrix. In this case, because we have this special example, it's actually identical to the controllability matrix. Okay, and we can use the rank as well. However, this is a simple minimal case because you can see that the dimension 2 is the minimal dimension. It equals the dimension of the transfer function. And not that, but this is the lowest dimension because the ranks of these two matrices is 2. So here, the dimension of the denominator, the degree 2, is actually the minimal realization. But notice, look at the transfer function, look at h. You see, this is an irreducible transfer function. That's why this is true. Now let's make this function not irreducible. Let's amplify this function by s minus 1. By s minus 1. Okay? Right? How do you do that? So you need to multiply n and d with s minus 1. Now, polynomial multiplication in MATLAB is equivalent to which function? People in control should know. How do you multiply two polynomials in MATLAB? Do you know? Shoot. Do you know how to multiply two polynomials in MATLAB? I was asking you.
Conv.
Exactly.
Function.
It's a convolution. It's a discrete convolution. Very good. It's conv. It's a discrete convolution between two vectors. Conv. Okay. And D1. Very good. Conv. Did you remember or did you check it on Google? You can be frank with me.
I check it now.
On Google. That's very nice. It's conv. Yeah, that's the advantage of this internet. You can easily find whatever you like. But it's good to remember because you are control engineers. You should know these things. Okay. So look, I think this is correct. Yeah. So now let's have H1, or let's have HR from reducible equal TF N1 D1. You see, it's this one. So this is reducible by s minus 1. And now let's build, once again, let's build the system again. So here, I would say I will call them non-minimal. NM, NM, NM. D is not changed, is not important. D is the same. Okay. And here, N1, D1. Okay. And then you have sys non-minimal. You have sys non-minimal. Sys non-minimal. It's not minimal because you have the simplification. NM, 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 D. And then you build these guys. NM, 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 and you check the ranks. Yeah. So rank R NM, rank Q NM. Okay, let's see what happens, shall we? So now you have a third order. You have a third order controller canonical form. Look, you have a third order controller canonical form from this transfer function. You can check it here. Okay, D is 0, so it doesn't matter. Okay, and here you have the system. Now the controller bit. How come it's 3? Why is it 3? Because I made it non-minimal. Oh no, look, no, sorry. It's a controller canonical form, you see? Controller canonical form, so it's controllable. You see? 3 is the dimension of the system. 3 is the rank of the matrix of the controllability matrix R. Hence, the system is controllable. Yes, the answer is yes, the system is controllable because the system is in controller canonical form. However, look, the system is not, this realization is not observable. So this means that this realization is probably a non-minimal realization. This guy is non-minimal. You see? Look. Now, how do we extract the minimal part? Because the system is controllable, we extract the observable part. And since the system is controllable, anything of dimension less than the dimension of system is still controllable. Any way you cut those matrices, they are still controllable. Okay? However, now we need to extract the observable part of dimension 2. And let's look at the OBS. Look, you see? Decomposition. Composition. Okay? So this guy is showing you the observable and the controllable part. Yeah, it's showing you those puzzles, those tolerance puzzles. Okay? So we go back to our script. We go back to our script. And here we are going to get the A observable, B observable. No, it's actually no. It's the R, it's A tilde, B tilde, tilde. I don't know what T and K are, but let's leave it like this. Of A and M, B and M, and C and M. And the tolerance, what is the tolerance actually? Oh no, I don't need the tolerance. I just need the simple form. Okay, so delete. Look, this is the coordinate transformation. And here we'll probably find somewhere, look at how these matrices look like. So probably here we have to identify, look, you see? So the observable part. Here we have to identify the second, it's of dimension 2. It is of dimension 2. Okay? So the observable part is of dimension 2. Look, it's here in this corner. In this corner without the 0 here. This is, and this is. This is the observable part. This is the observable part. Okay? All right? So now we get the minimal realization. Let's anticipate a little bit. Let's anticipate and use the mean real. Okay, so this is using, again, these functions, OBS VF and CTRBF, are using a very efficient numerical algorithm to compute the observable or the controllable decomposition. Now we can get the the observable part, A0, B0, C0, D, I think you must have D, is mean real of cis NM. Let's see if this is correct. Oh no, this is not correct. Too many arguments. Let's do some help. No, this is not right. This is right. Mean real. Oh, okay. So M-cis is mean real of cis. Fine. And here you also get the coordinate transformation that yields the Kalman decomposition, the structural decomposition. The structural decomposition is also called Kalman decomposition because Rudolf Kalman is the American who discovered it. He's dead now, but he got from President Obama a big medal for achievements in control theory, because his Kalman filter and Kalman, these are widespread over the world, so they are fundamental now. They're fundamental now. So minimal cis is mean real cis NM. Okay, it's computing. So look, this is the minimal realization. Let's see, minimal, look, you see, it's this part. Do you recognize this part? Here, it's the minimal realization. This is from the structural decomposition. Okay? Minimal, so the observable part, which is now minimal, and we'll see about that next time. And this is the coordinate transformation used to build the decomposition, which yields the observable part from the non-minimal system. Is it a bit clear of how these things work? This is my question. Is it a bit clear?
Yeah, it is clear.
What I advise you to do is build up and play with these things. Play with these things. Play quite a lot in MATLAB. You do not need to understand the theory. Try to solve a lot of these things using the MATLAB. To understand, to grasp the meaning of controllable, observable part, controllable part, structural decomposition. Try to understand these things. Okay? Try to understand these things. Okay? Yeah. One more thing, we can compute the infinity time Gramians as well. I forgot to mention that. So for the non-minimal here, we can compute the Gramians, or for any system. So LC, the controllability Gramian, is the Lyapunov of A and M, and B transposed. Not transposed, B transposed like this, and LO, the Gramians, because I forgot to mention the Gramians, they are going to be very important also next time, these Gramians. Liap of A and M transposed, look at the Lyapunov equation for the controllability Gramian, C transposed C and M, sorry, and M, and M, and M, and M. Let's look at the Gramians. Look, controllability and observability Gramian. Are they positive matrices? Let's look at the Eig, because these are small matrices, then we use other efficient stuff with call. Yes or no? Why not? Should be, oh, because A is not stable. Because A is not stable is not positive definite. Sorry, because A is not stable, it's not positive definite. True. The same will hold for the observability gradient. So we have to do it for the observable system, for the stable system. So we take these two and we go to the second order system. We go here. We go here and we use AM. Again, F5. So now let's look at the gramians. Where's the gramians? Oh, here they are. So these are positive. These are definitely, look, this one you can easily see it's positive definite, LO, and LC. Okay, so because the system is asymptotically stable, all the eigenvalues are in the open left half plane. These gramians are also positive. So you look AG of LC and AG of LO. Okay, so they are positive definite. These are the gramians. Gramians are very important. So if the gramians are positive definite, then the system is controllable. If the observability gramian is positive definite, the stable system is observable. Okay? Fine. Questions? If you have any questions. Do you want me to upload this file to the Teams?
Yes.
Yeah,
Victor.
Let me just try. No, I was looking for something else. I was looking for this. Files. Okay. There's nothing here. So we can take from here. We can go here. We can go here. We can go simulations. Yes. And you can get, actually, I'm going to put all the files here. You can play with all the things we have been doing so far. Look. It's 10 files, okay? All right. So you have the files here. Please understand and try to do as many exercises. I know you haven't got time. I know so on and so forth. Do the assignments, do some exercises so you can understand the model reduction techniques we are going to learn quite soon. Okay? Because it's actually research. You'll have to learn them. I'm going to give you some general ideas and you are going to have to read in the book and in the papers. Okay?
okay.
Okay. If you have questions, please. If you've got any questions, please. If not, I think that's kind of enough for today. If you need me to tell you anything else, because we still have quite a portion of time, please feel free to tell me. Questions, please.